Okay, we are not going to cover any new material today. We are just going to talk about proofs, proofs, and more proofs. The way we get good at it is to practice. But a quick review of triangle congruence, which is the heart and soul of this chapter. Which property proves these triangles congruent? And basically you have 5 choices or none. Number 1 can be tricky because it looks like we have congruent sides, except they're congruent within the same triangle, not between the 2 triangles. If we laid these 2 triangles on each other, they would not match up. So this one is none. Here, right triangle, I know the hypotenuse and a leg. These guys are congruent by HL. Don't forget, you can always mark vertical angles on the reflexive side. So this is congruent by angle, side, angle. In number 4, I have a reflexive side. So when I mark that, I see I have angle, or I have side, angle, side, which corresponds to the other side, angle, side. In this case, I do have corresponding sides and angles, but remember, there are no potty words in math. And so this does not prove congruence. And the last one is another right triangle. I know a hypotenuse and leg. These are congruent by HL. On to some proofs. Each of these proofs is a matter of piecing together the information. So we always write our given, mark our picture, and see what we have. Now I want to prove LMN. I'll give myself a little marker. I want to prove PML, this one, and OMN, this one. Well, whenever we're asked to prove angles or segments, we're almost always going to be looking at a CPCTC. So we want to get our angles, our triangles congruent, and then get our angles by CPCTC. When I look at my given, angle L and angle N, angle O and angle P, and this segment, I already have enough to say that the triangles are congruent by angle, angle, side. And I'm always careful. O and M corresponds to P, N corresponds to L, and M to M by angle, angle, side. Remember that congruent statement has to line up. Once I have those 3 pieces named, I bought 2 angles and I bought a side, I get the other 2 sides and the other angle for free, CPCTC. So I can say angle PML is equal to angle OMN by CPCTC. At any time during these proofs, feel free to pause, rewind, and listen to them again. That's what the videos are for. Given that AP is parallel to LN and PR is equal to NR, prove that PA is equal to NL. Now, PA and NL. One of the temptations is when you know the sides are parallel to assume that parallel and equal are the same thing, and they're not. Butterfly pictures very often have this parallel piece, and as soon as I see parallel, I need to start thinking angles because parallel lines give me angles. So in this situation, mark this, we know it always helps to extend our parallel lines out so we can see them better. There are actually 3 different ways to do this proof. My butterfly picture, I have vertical angles. I'm going to do those first. PRA is congruent to angle NRL by the vertical angle theorem. Now with an angle and a side, I'm looking for either angle, angle, side, or angle, side, angle. When I use my parallel lines, and if I use this as my transversal, I can see that I have alternate interior angles right there. So I have angle APN is equal to angle LNP. Oops, kind of messy, LNP, because parallel implies AIA. I know parallel, it gives me alternate interior angles. My picture is marked. I know now that triangle PRA is congruent to triangle P corresponds with N, R corresponds with itself, L with A. That is by angle, side, angle. I know two angles and the included side. And then PA is equal to NL by CP, CTC. You could have also used this line as your transversal, and that would have given you these alternate interior angles. So from there, you could have done angle, angle, side, or you could have done angle, angle, side. All would have been correct. Proof number 3 in this lesson, a little more complicated, and this is where proofs get fun. This is a matter of really needing to look at the picture. There are actually 3 sets of potentially congruent triangles, and I'm going to mark them first. So I have this overlapping triangle and this overlapping triangle that I could be working with. I have the bottom overlapping triangles, this one and this one I could be working with. Or I have the butterfly triangles inside that I could be working with. This one and this one. Which of those triangles I need is all going to hinge on what I'm given and what I need to find out. So let's look at what I need to find out first. I am trying to prove 3 and 4 are equal. Now, unfortunately, those are a part of my overlapping triangle CBA and DAB. But if I drew them out separately and looked at them like I did in class, I don't have enough information to proceed. So where I need to start is with the butterflies. So I know angle 1 and angle 2 are equal, and angle AC and angle BD. And when I mark those, it's clear to see that I'm closer to proving those 2 triangles congruent than any others. How that helps me, we'll see in a minute. Like I said, this is more of a challenge proof that's showing you how you can move beyond just the CPCTC. Butterfly proof, we always have vertical angles. So angle AEC is equal to angle BEC. This is a fold in half proof. Now, I have enough information to prove my blue triangle is congruent. So triangle AEC is congruent to triangle BEC by my picture, angle, angle, side. Now, you might be wondering how that even helped us. If I go back and I use my highlighter and I look at this triangle right here, because that's where my green, my 3 and 4 angles I'm after, are related. 2 of the sides that make that yellow triangle are part of the blue triangles I just proved congruent. This side right here and this side right here. So I know I can say that AE is equal to BE by CPCTC. And if I look at that triangle that's in yellow, AEB, I see now it's isosceles because of the CPCTC sides. And what's true about isosceles triangles? Well, their base angles are equal. So angle 3 is equal to angle 4 by the isosceles triangle theorem. Because in step 4, I said the sides were equal, making it an isosceles triangle, then I get that the base angles are equal. So while it looked complicated, Really not that bad of a proof. Now, number 4 also looks complicated. There are 3 sets of potentially congruent triangles here. We have little guy on top and a little guy on top. We could do the little guys on the bottom. This one and that one. Or we could do the halves. This and that. Again, it depends on what I know and what I'm being asked to prove. What I'm being asked to prove is that this side is congruent to that side. That means I'm going to need either the bottom ones or the halves. Well, what am I given? I'm given that xy is equal to xw and that zx bisects the angle, which is this one and this one. So it looks like I'm going for the halves to get those bottom yellow pieces by CPCTC. So yx is equal to wx, and zx bisects angle yxw. Make sure you always are reading the direction of that bisecting statement and only bisecting the direct object of that verb. So if I'm looking at my big triangles, and I'll go ahead and color code them for us, looking at that one, and I'm looking at this one, I can see by my marker that I have that reflexive side. xz is equal to xz. It's a fold in half proof by reflexive. When I mark that, I can see that I have my big triangles congruent. Triangle ZYX is congruent to triangle ZWX by side, angle, side. And then my yellow pieces, YZ is equal to WZ by CPCTC.